Thank you very much. So first of all, I'd like to thank the organizers for inviting me and for putting together this lovely conference. It's my first time also in India, and I'm enjoying it very, very much. And so thank you for that. And can you hear me well like this? Okay. So what I'm going to talk about is, as the title says, the propagation of Lagrangian states. So in particular, we'll be interested on certain functions. I will describe what these words mean on hyperbolic manifolds, and we'll try to propagate them under the time evolution with respect to some Schrödinger type equation. And the potential, in a sense, in this Schrödinger type equation will be random, and we'll try to understand some sort of delocalization properties. So let me say that this is what I'm going to talk about is joint work with Maxime Ingremont from the University of Côte d'Azur. So this is him. He looks very confident. And so I'll like to start out with some background and motivation, so why we're interested in these sorts of questions. And in a sense, let me present this setting. So one of the big sort of motivations for this is this field of quantum chaos. I mean, you have already maybe seen this in the talk of Nikhil, where he asked similar questions for sort of on the setting of random graphs. But here what we are looking at, so just for motivational purposes, I'll be looking at X to be some bounded domain in RD, but in general, we'll be having X to be a compact Riemannian manifold, and for later purposes, it will be of negative curvature. So what we'll principally have is minus Laplacian here, which is said to be positive, just as so when we're on this bounded domain, it will be the Dirichlet realization of this Laplacian, and on this compact manifold, it will be just the Laplace-Beltrami operator with respect to the metric G. So what is the sort of questions that we're looking at? So we're considering eigenfunctions and eigenvalues. So I mean, this is the spectrum, because the manifold here is compact, or the domain is bounded. I mean, the spectrum is entirely discrete. So we're having these lambdas here, which is just a sequence growing to infinity of real values. And with each lambda j comes an eigenfunction, psi j. And so they're giving us an orthonormal set of eigenvectors that span essentially the space L2. And here they're set to be in L2 norm 1. And the questions that we are asking is, so how do these eigenfunctions behave in this high energy limit? So as lambda j goes to infinity. Okay. So in a sense, so we want to study, well, in this probabilistic interpretation of quantum mechanics, we want to study this probability density that is given by the modulus squared of this eigenfunction x as j goes to infinity. So as the index of these eigenvalues go to infinity. So for example, we could be interested, can it be that these eigenfunctions or this probability density concentrates somewhere on X, on my manifold or my domain, or does it kind of equidistribute? Is there a sort of delocalization phenomenon going on? So in one way to kind of see this would be, I could ask, well, if I take some bounded subset here and I kind of measure my density here on the set B, as j goes to infinity, does this converge in a sense to this uniform measure? Okay, so that would be one form of equidistribution. And so what is going on? So here, similar pictures I think you've seen in the talk of Nikhil. So quantum chaos on billiard. So here, this is two bounded two-dimensional domains. One that is in a sense where the sort of classical dynamics is regular. So this, or integrable for that matter. So by classical dynamics, you have to imagine like a ball bouncing around that unit circle. And every time it hits a boundary, it gets reflected due to the law of equal angle, essentially. So the incoming angle is reflected to the outgoing angle. And so the way these sort of trajectories of this classical dynamics look in this regular domain, completely different to this cardioid here, where essentially the sort of classical dynamics is chaotic in the sense that it's ergodic. And so the basic idea of this sort of quantum chaos is if we have an underlying classical dynamical system that is chaotic, how does this reflect in the behavior of the eigenfunctions? So the hope is essentially to understand some kind of equidistribution property of the eigenfunction. So in fact, if we look at this, so for this regular domain, so if we look at eigenfunctions of the Laplacian in this circle, they have a very regular distribution, whereas the high energy eigenfunctions in this chaotic domain, they become, in a sense, much more chaotic themselves. So they get much more equidistributed, and whereas this one here can be very much concentrated in certain sets. Okay, so these pictures come from Michael Barry. And so on the other hand, so the second setting that we'll be looking at is on these negatively curved manifolds. So here's just an illustration of some sort of genus 2 negatively curved surface. And also in this case, if we're looking at the eigenfunctions of the Laplacian, they will look pretty much like this. So what you're seeing here is, so this is for an eigenvalue of 5,000, so rather high already. So this is essentially this genus 2 type surface cut up. And here what you're seeing is, according to the height, so blue and these cold values are essentially where the eigenfunction takes very small values, negative values, and kind of yellow until black is where it takes large values. So you see essentially that it's, I hope you can see it well, that it's essentially starting to be very equidistributed. So it's this is for the high energy eigenfunctions. And the same picture here with the sort of nodal lines. So here I hope you can see these sort of black lines that separate the yellowish tones from the blue tones. So this is exactly where this eigenfunction hits 0. Okay? So this is essentially what Neil investigated in his talk. Also, these pictures come from Alexander Strohmeyer. And so here you can also see already this sort of equidistribution phenomenon that essentially, if we're looking at these eigenfunctions on this hyperbolic or this negatively curved manifold, and here in a sense the classical dynamic would just come from the geodesic flow. So where you, in a sense, evolve a classical particle along the lines of simply along geodesics determined by the geometry of your manifold, which is chaotic in a sense, or ergodic since we are negatively curved. And here you can see in this sort of illustration that this reflects very well in sort of an equidistribution phenomenon of the eigenfunctions. Okay. So one of the, by now, classical theorems of how to properly measure this equidistribution is given by quantum ergodicity or quantum unique ergodicity. So this theorem goes back to Schnirelmann, Zeldich, and Colin de Verdière. So it states essentially that, so what are we looking at? The psi j's are the eigenfunctions of the Laplacian on this negatively curved compact manifold. And here we are trying to kind of measure them against some sort of test function AX. So we are localizing them just in position. So interesting, like how does this eigenfunction look like at this tested against this function AX? And this d volume here is just the Riemannian volume with respect to the with the metric g. And so here this theorem tells us that so there exists a density 1 subsequence of these j's. So that means that essentially most of them, you have to extract a subsequence, but most of these eigenfunctions, we have that this converges to simply the uniform measure on this hyperbolic manifold as j goes to infinity. So this is not the full strength of these theorems. Actually, you can measure them not only in position, but also in frequency. Okay? So you could also understand that if you take the Fourier transform, that in a sense the distribution of their frequencies in phase space get equidistributed. So, but I just presented this simpler version. And yeah, so there's been a bunch of conjectures later on, because it is kind of, first of all, the question is, as conjectured by Rudnick and Sarnak, that actually, since we are working on a negatively curved manifold, that it should, and the chaotic or the nature of the chaotic classical, or the classical dynamics is rather chaotic, rather strongly chaotic. They conjectured that actually this sequence should not only hold for a density 1 subsequence, but for all eigenfunctions. So the full sequence of eigenfunctions should converge, and they're not is not a subsequence of eigenfunctions that tend to concentrate near some point or some geodesicus. There has been a lot of work in that direction. Like the literature is huge. I cannot name all of them, so I apologize. I tried to name some important recent works that kind of try to prove this conjecture. For these stadia, for these two-dimensional domains, it was proven actually by Hassel that for certain domain stadia, this quantum unique ergodicity, so that it holds for all eigenfunction, fails. Maybe more interesting to you guys here, there's this kind of understanding or this way of measuring delocalization has recently also been used very much in random matrix theory. So there was work by Bourgade, Jin, Benini, and Cipolloni, Erdős, and Schröder, who considered the eigenvectors of Wigner matrices, generalized Wigner matrices, and they showed that a pendant, like a similar notion of this delocalization, this way of understanding delocalization holds. And also similarly on deterministic regular graphs, this form of delocalization has been shown by Nanterman, Le Masson, Fuchs, Lindenstrauss, Nanterman, and Sabri, and on regular, random regular graphs by Bauer-Schmidt, Knowles, and Yao. So there's various works to understand this form of delocalization. So before I tell you exactly what this talk is going to be about, so this was roughly the setting. I'll just do a sort of brief introduction to one of the major tools, which is semi-classical analysis. So the first one is simply a sort of semi-classical rescaling. So on the one hand, we considered these eigenfunctions with the eigenvalues lambda j of the Laplacian. And so we're doing a semi-classical rescaling. So we're putting hj simply to be 1 over the square root of this eigenvalue. And by this rescaling, we end up with this semi-classical equation here with 1 minus h squared Laplacian minus 1. So the eigenvalue is just 1 times this eigenfunctions that equals 0. And instead of considering the large energy limit, we're considering the semi-classical limit as h goes to 0. Okay? So this is just in a sense for convenience. But we'll need a little bit more tools from semi-classical analysis, and that is how to this notion of semi-classical pseudo-differential operators or semi-classical quantization. So it's a brief crash course, but so let me just remind you in a sense. So on RD, we can consider, for example, multiplication operators by a smooth function. So just sending u to the multiplication by u by p. But also I could consider differential operator, which is just I take this differential to some power alpha and d of some function u that is suitable differentiable. But I mean, I can generalize this idea of taking these differentials to what is called a Fourier multiplier. So in a sense, I take a function p that is say smooth, and in a sense, I take the Fourier transform of my function. On the Fourier side, I multiply my function, my Fourier transform function here with this function p, and then I go back to position space. Okay, so this is essentially a generalization of more general functions here than just the powers of psi. So this would correspond to a power of psi, and this is essentially the fundamental idea what I can do with a pseudo-differential operator. It's just that instead of considering functions here that just depend on psi, I will also let them depend on x. And an easy example is essentially this: if I have some function that is a polynomial in the frequency variable. So this is a function now on R2D. It's a polynomial in my frequency variable, and times these coefficients here, there will be just smooth function by x. So if I apply the Fourier transform, I would get that this pseudo-differential operator in truth is just a differential operator of this form. And on compact manifolds, I can do the same, and we'll call it later on. So once I don't consider R2D here, but instead I'll consider the cotangent space of x, so my position space, and in the fiber variables, that will be just psi. Okay? So I can, and the advantage of these sort of pseudo-differential operators is that I can, so here if I multiply by a function in position, that means I could localize a function to some small neighborhood in my position space. But the advantage of pseudo-differential operators is essentially that I can localize them at the same time in position and in frequency to really analyze how functions behave in position and in their frequency variable. So that is essentially it. Okay, so what I'm mostly trying to focus on is a slightly different form of delocalization for these eigenfunctions, which is related to this Barry's conjecture. And the Barry's conjecture essentially will tell us that, well, in this high energy limit, a good model for these eigenfunctions is in fact a sort of random wave model. Okay? So these random waves here, for example, we can consider this, this function here of x, where we just take a sum from 1 to n and we normalize it, and times these oscillatory parts here. So we take ei, say, psi k times x, so x is a vector in Rd, and psi is just a uniform, random variable uniformly distributed on this d-1 sphere. And the phi k's are uniformly distributed on 0 to pi IID. So this would be a nice model for a sort of random plane wave on Rd. And I mean, there is a huge literature connected to the study of these random waves. How do they behave? How large are their nodal domains? So the domains essentially where they are 0. And I could not cite all the related results, but there's a recent survey by Igor Wigman that you can find on the archive that covers a lot. So what is Barry's conjecture? So Barry's conjecture essentially, I mean, it was formulated much more generally, but in any case, a little bit open to interpretation. So in our setting, it would say that, well, the eigenfunctions of the Laplacian on a classical chaotic system, so as this cardioid, for example, or on a hyperbolic manifold, should in truth, in the semi-classical limit or in the high energy limit, look like, strongly resemble these sort of random wave functions. Okay? And indeed here, I took a picture from a paper of Vogel and Schmidt. So on the left, you see a high energy eigenfunction, so the nodal domains of a high energy eigenfunction. On the right, you see essentially a random plane wave like this plotted. And they conjectured this essentially, I mean, these two plots look the same. It's hard to see the difference. So, but unfortunately, I mean, Barry's conjecture was not formulated very precisely. It's in a sense just like they should resemble each other. So one of the tasks is to find a good way of making this precise, what we need to prove. And so first, what I'm going to introduce is this. So let me talk about an interpretation, or one possible interpretation of this Barry's conjecture. So what I'm going to introduce is this, what we're going to call this Barry Gaussian field. Okay? So this is just a normalized monochromatic stationary isotropic Gaussian field. So with this normalization constant lambda here, it's determined by its covariance kernel. This covariance kernel is essentially here just given by this integral over EIX minus Y psi, and this is the uniform measure on the SD-1 sphere. Okay? And so this is essentially a nice limiting model for this random wave that we saw before. I mean, there's multiple random waves that you could construct that converge to this, but the one I showed you before would converge in distribution to this Gaussian field. And so this is essentially would be a nice limiting object that we would like to see that our eigenfunctions in some sense converge to. Okay? So monochromatic here, sorry, just means that if I take this sort of field that it's almost surely it's an eigenfunction for eigenvector 1 of my Laplacian. So this one interpretation that we're going to use in this talk is, in a sense, a local limit. So this idea goes back to Ingremont, my collaborator, and also Habert, Bergeron, and Le Masson. And the idea of this local limit is essentially motivated strongly by the Benjamini-Schramm convergence on random graphs. So the idea is I take my manifold and I pick a random point, essentially, say uniformly at random, and I look at how does my eigenfunction look in a small neighborhood around this point. And the idea is that, well, so I'll describe this a bit more precisely, but the idea is, if I, at the local scale, so the local scale will be described by my small parameter h, but does this eigenfunction after rescaling converge in some sense to this Gaussian field? Okay, so this would be this interpretation. So let me make this a little bit more precise. So what we are doing is, so this is my manifold. I just take a sufficiently small open set, and I want to compare it with a random function on RD. Okay, so I just have to make a little bit of a geometric construction to kind of look at this as a function on RD. So what we're doing is I take a small set, and in this set I can find an orthonormal frame. So an orthonormal frame, this is just d different vector fields, so sections on my tangent bundle, smooth sections of my tangent bundle, such that this d tuple here, so the manifold is d-dimensional, so that for each x in my little domain, this d tuple here is an orthonormal basis of my tangent space. Okay? So this frame, this is just a technique that if I start varying my point in the small domain, that this frame, so these d vectors essentially vary with my x and always give me an orthonormal basis. And then the next step is I'll take the exponential function. So here this exponential function at x of y. So I define this to be this more well-defined. So this is a brief notation for this guy here. So for a point y in Rd, I just look at what does the exponential function give me if I essentially multiply v1 by y1 and so on and so forth. Essentially, I know that this exponential map around the point x is just a nice chart, essentially. Okay? And I'm just making this so that with this frame, such that if I vary x in that neighborhood, it still remains a well-defined chart. Okay? So long story short, so the idea is that if I take now a family of functions that are smooth functions on my manifold, and I take x, so this kind of script x to be a uniform random variable on my domain U, I get this random function fx of y, so y is in Rd, just by composing my function, my family of functions on the manifold with this exponential function. So this is just a way of describing what good coordinates in a sense. And this local limit, what I really want to prove is, so I say that some probability measure on the smooth functions here is this h local weak limit. If after rescaling by h here, this converges in distribution to this probability measure. So the law of this function converges to this probability measure. So that is this idea of this local limit. Yes? These guys here? No, here there are functions, but what I mean here is that they converge in distribution. So the law that, okay, so there is a random parameter, sorry, the random parameter is this point x here. Because I pick, here I mean the density. So essentially you pick a point at random, and so this gives you a nice well-defined random function, and you want that this sort of law converges to, essentially we would like that this converges in distribution to this Gaussian flow. The frame, I mean, in this construction, it does depend to the frame, but I mean, the limit, you don't see the frame in the limit. So the limit, it does not depend on the choice of frame. Yeah. This is, okay. Any other questions? No? Okay. Cool. Yeah, so, but this is in general very hard to do for eigenfunctions, so we're doing some simplifications. So the first simplification is that instead of considering eigenfunctions, we're considering Lagrangian states. Okay, so this was in the title. So these Lagrangian states, they look like this essentially. So you have a sort of amplitude function A of x, which is just a smooth function of compact support, and you have this oscillatory part. So I over h, phi of x, and phi is some smooth function, this phase on U. They are good models in a sense for these eigenfunctions, because essentially if you want to construct an approximate eigenfunction for your eigenvector, then you would essentially construct these sorts of functions. I mean, they themselves will not be eigenfunctions, but typically a lot of linear combinations of these sort of guys here will give you excellent approximations or quasimodes for your eigenfunction. associated with this function here essentially is what is called this Lagrangian manifold, which is just a submanifold of my cotangent space, which is just the graph of the gradient of this phi. Okay? And I'm only insisting on this submanifold here for the reason that, for two reasons essentially. So in terms of H, my function is really localized to this submanifold. So in position and in frequency, if I go away from this submanifold, my function will be negligible. And monochromatic here that I used here simply means that, in fact, this is not a submanifold of the tangent space, but of the cosphere bundle. So the gradient here is always of length 1. And the second simplification is that we are not considering exactly how do eigenfunctions behave, but we're just, in a sense, time evolving these Lagrangian states. Okay, so we're looking for long time evolutions under the Schrödinger equations of these Lagrangian states. In a sense, so here we're doing a certain simplification, because if this f of h were a genuine eigenfunction, and in the Schrödinger operator here, P alpha of h, where I take the Laplacian plus a sort of small perturbation, I'll describe that in more in detail in a second. If this were not here, okay, so if Q is 0 and this were an eigenfunction, then essentially here, simply by the spectral theorem, I just get a little oscillatory factor. So an eigenfunction would ignore this. But the genuine idea is to try to understand these kind of, for long time behavior, for large times t that depend on h, to understand how this time evolution of this function f of h, which in a sense is a nice model for a genuine eigenfunction, to understand, does also this sort of function verify this Berry's conjecture, or our interpretation of this Berry conjecture? So does this converge in a sense to this Gaussian field? Yes? So in a sense, it's not a generalization, and I mean, in a sense, it's more like a model to try to understand what is going on. In a sense, there is, so for eigenfunctions, so for eigenfunctions, so if you would take a general eigenfunction, this sort of, and without this random part here, this does not have any effect. So usually you can try and when you analyze these sort of propagators, you will try to understand via this propagator how far distributed your eigenfunction is. Okay? Because here, in a sense, you have to think it like this, that so if you take, for example, f of h something simpler, like a Gaussian wave packet, you know, something that is really localized to a point. So in position away from a point, in a sense, it decays exponentially, like Gaussian, and in frequency, it is also localized to a point. So if you apply this propagator to it, what happens is, so this propagator without this random part, okay? What happens is it simply, as time evolves, you will start smearing out this localization. So really, it stops being localized to a point, but it really gets smeared out and localized along essentially these geodesics along here which evolve. Okay? So in a sense, this is simply trying to figure out a little bit what is going on here, and to come up with new ideas how to try and tackle this Berry's conjecture. But so what this in particular, this model is to, I'll discuss when I'll get to the theorem a bit what has been done, but in general, in our model, what we are adding here is this sort of random part. So it will be a sort of random Schrödinger operator, but this random part is very small. So in a sense, we put an h to the power of alpha between 0 and 1 in front of it. So this is really a genuine small perturbation with respect to this Laplacian. And so what will be this random perturbation? We'll take two types of models, okay? And essentially, the first one is simply a bit motivated by the Anderson type models. So this, either we're taking Q to be a genuine random potential, meaning that these chi's here, there's just bump functions, okay? So compactly supported bump functions that we translate around. So this rho should be an x. So we take points x, j on our manifold, okay? And a bunch of them, And we look at, after scaling by 1 over h beta, beta is, oh yeah, here it is. It's between a value between 0 and 1. And this is the distance function of my point x to xj. So what I'm doing is essentially this for this random potential. So I have here my manifold. I'm plastering this, I'm covering this manifold with sort of small balls that are all centered at this xj. Okay. And above each xj, I get this sort of bump function. And the height of this bump function is essentially random. Okay. So just like in the classical Anderson model in physics. So we have this omega j. This is just a sequence of IID random variables that, for simplicity, here have bounded support here. So they take values in -1 to 1. And so this is then a multiplication operator. But we can also consider something a little bit more general in a sense, that is this random pseudo-differential operator. So the construction is exactly the same, but instead of taking these bump functions just to be on the manifold, I take them in phase space. In a sense, the noise does not only affect your function in position, but also in frequency. There's for completeness, there's a relationship between the size of the perturbation and beta, so that everything makes sense. I'll not describe this in detail, but I will simply give you this graph. So this is, the condition is non-void. So if I perturb with this pseudo-differential operator, I can take this parameter set here, and if I take just with the potential, I'm a little bit more restrained to this parameter set. So if I take alpha to be very small, then I can essentially don't take any beta, but as alpha grows a little bit larger, then I have a bit of a choice of all my beta variables. And just to insist on that a little bit, so beta here is essentially the oscillations of your potential. Okay? So your potential will oscillate at frequency h beta, and it will be small. Okay. So with that in mind, what can we prove? So I put this random propagator, this random Schrödinger operator up there, and so what we can say is so that if I take any sort of open set and any orthonormal frame, let this be such a Lagrangian state. I take a time that depends on h that goes to infinity, but not faster than log of h. So it can go to infinity, but it shouldn't go faster than log of h. Then for all x that is in my manifold, I will consider 2 types of convergence. So for all x that is in my manifold, away from a set of x naught, and the x naught has volume that goes to 0 with h, so it's a negligible set in a sense of some problematic points. Essentially, this propagated, so if I apply this propagated to my function and I do this local rescaling, this converges indeed to this Gaussian field with a sort of normalization constant that I'll give you in a moment in distribution. However, this sense of the convergence is for a fixed x. So here I look at the specific x, and I look at this convergence with respect to the random variables that, in a sense, I artificially introduced through my perturbation. And the second thing we can prove is that now if we take sort of that there exists an epsilon such that for all bounded continuous functions on this set of so test functions on my set of smooth function on RD. So I integrate essentially this test function against this process here. With respect to the uniform measure on X, minus this, here I integrate this test function, I take the expectation with respect to the law of this Gaussian field. And that in probability with respect to beta, this is smaller than h epsilon with extremely good probability. And essentially this normalization constant here that appears in this Gaussian field just depends on A of, so the amplitude in a sense, which in a sense is simply the L2 norm of my Lagrangian states. Related results maybe that so there's a lot of results that are somehow related, because in 14 and 16 by Bourgain and Buckley and Wigman, essentially they proved this Paris conjecture 4 toral eigenfunctions with some strong arithmetic arguments. More recently, for this sort of Barry's conjecture, there was a work by Angremont and Riviera who proved that this theorem holds. Essentially, you have this convergence to Barry's conjecture without any random potential, but the price they pay is that they cannot do it for all Lagrangian states. And if you want to kind of think of Lagrangian states to be good models for eigenfunctions, you cannot restrict the phase, because the phase will be essentially determined by this approximation procedure. So they had this sort of genericity argument. And just to relate these results also to the idea because proving this quantum unique ergodicity is a very hard problem. So people generally came up with the idea of, well, we could try and add small randomness or large randomness or anything to kind of try and extract new ideas or mechanism how to prove this quantum unique ergodicity. So in a sense, there's related results where by Chatterjee, Galkowski essentially, who showed that if we take eigenfunctions of an arbitrarily small perturbation of the Laplacian, but there they actually perturb the Laplacian and they don't just add a potential. Okay, so they genuinely have to, by hand, perturb the Laplacian so that in a very, in a sense, constructive way, so that the eigenfunctions would satisfy this quantum unique ergodicity. And maybe just to mention it, another way of like measuring delocalization of these eigenfunctions is with bounds with respect to LP. Okay, so this large LP, and there actually, so there's this work by Eswara Hassan, Roth, and Kanzani and Jacobson, who propagated eigenfunctions by Schrödinger operators, but with a potential that is essentially of order 1. So not quite comparable with us, where we just add a tiny noise. But they gained improved LP bounds. So in a sense, it's related works. So with that, in the rest, I would just like to try and describe you a little bit how we can prove these sort of things. And so the first step is essentially what is called a WKB construction. So we try to understand how does this Lagrangian state, if we apply the propagator to it, how does it look like? And the first thing that is a very convenient, essentially trick, if you want to, is that instead of working on X, we work on its universal cover. So I got this graph here from Wikipedia for the universal cover, and I think it illustrates it quite well. So you have your base manifold here, and the universal cover is just a simply connected, in a sense, larger manifold, such that where each of any set of your manifold gets repeated, okay, such that if you project it down, all of these sets get projected down by this surjective projection onto this one set in your base manifold. So I'll explain a little bit later why it is more convenient to lift everything to this covering and work there and then project it down again than to work on your space X. So we start out with this phase, and we make this WKB ansatz. Which consists in the sense by following. So we have this thing to analyze, which is this propagator applied to this Lagrangian state. And for convenience, I will call this perturbation size here, which is H alpha, I will call it delta. So the idea of this WKB ansatz is just the following, that you make this ansatz that this guy in truth looks like this function, where there is an oscillatory part, and then there is a sort of expansion into powers of h and functions that can depend on this parameter delta, but they're essentially smooth functions in t and x. So to make this ansatz, what you want to do is you want to take n in a sense sufficiently large that the error term that you're doing between this propagated, this actual function, and this ansatz is very small. And to do this, well, to say that to compare the two of them, we want to construct it in such a way that this u tilde solves this Schrödinger equation. So this means what you do is you plug in u, you take your derivatives, you apply the Schrödinger equation, and then you order what you get in terms of powers of h. Okay? And then just you get a bunch of equations that you need to solve, and if you can solve them iteratively, then you get a very good approximation here. So the 0th power of h is also what we're going to mostly be focusing on, is this called Hamilton-Jacobi equation. So this is essentially just that the derivative with respect to time of this phase here has to be equal minus to this function p, which is essentially this what is called the symbol of this operator here. If we were to quantize this with our sort of pseudo-differential operator procedure, we would end up with this operator, essentially. And so, but what you see here is just that in frequency, it's just psi, this norm to the power of 2 of my frequency variable x. So this is essentially what is coming from the Laplacian, plus this small perturbation part. So this is the sort of random potential or random pseudo-differential operator that I constructed. And then these B zeros here and the BNs are determined iteratively by some sort of iterative procedure that you can solve one after the other. So I will mostly focus a little bit on this equation here because there where you see what is going on a bit. So this is essentially the equation that we need to solve. So we have this time derivative, we have this function p, it needs to be equal 0 with some initial condition that at time t equals 0, it has to be the initial phase. Yes. Yes. It's still formal, but so in the sense what you keep track of is the arrow term. So if you're doing this ansatz, the idea is essentially that here you're making an if you do this, you may make an arrow term that will depend on the large n. So you've solved all these Bn in essentially that for all the powers of h, this solution is exact, but just you will get the last term there, you will make an arrow, but it has the h to the power of n in front of it. So if you control well these solutions, you will gain powers of n in h, and h is small. And n can, in a sense, be taken arbitrarily large. So if you continue this procedure for a very long time, then essentially you can make your arrow arbitrarily small. So you can think of it in the two ways. So either like purely formal, or I mean, with this keeping in track of the arrow term, you can make it exact. There is no problem. So to solve this, so the interesting bit here is this Hamilton-Jacobi equation that we need to solve. And to solve this, essentially, there is because this guy here, this p, it does depend on the randomness. So essentially, this is this psi. I rewrote it here, psi squared with respect just the Riemannian metric plus this random potential here. And to solve this guy, what you do is, in a sense, a geometric construction. Okay? So to solve this, you consider the flow that is given by this Hamilton vector field, HP, that is just written here. So you take the derivative of P with respect to any sort of, this is written in canonical coordinates. So with respect to any psi k times the derivative d dxk and minus dp dxk times the derivative of dd psi k. So this gives you a vector field on the cotangent of your psi k. And let me just tell you that if the delta here is equal to 0, so this means that here in this function p, I take only the first part, then this Hamilton flow here would be essentially the geodesic flow. Okay, so this means that this, if you increase t, what you do is you propagate the particle just along the geodesics with a certain speed of your manifold. Okay? But we are in a sense having this perturbed field, so essentially this is this sort of, in a sense, a random flow that we need to study. And so to gain a solution for this, what we actually just can do is consider this time-evolved Lagrangian manifold. So lambda 0 was the Lagrangian manifold that is associated with phi 0. So this is just the manifold that is essentially the graph given by the gradient of phi 0. And if we apply this flow to this guy, so we just time-evolve this manifold, we get a lambda th, and here it is nice that we've been on this universal covering, because the thing is the following, that to define, so it's a classical theorem of symplectic geometry, that if this Lagrangian manifold projects well, so meaning that if I project it onto my base manifold, and this projection is a diffeomorphism, then I can represent it here again as the graph of a gradient of some function phi t. But for this, I need that it projects well in a sense. And there is the problem, because if we had worked with this guy on the base space, at some point, because this Lagrangian manifold, it will evolve, it will spread out according to the flow, and at some point it will cross itself. In a sense, it will wrap around our compact manifold and it will start crossing itself. And there, essentially, I do not project well onto my base space because I have a manifold that crosses itself. However, on my universal covering, this cannot happen. It will just evolve. And in a sense, what will happen is, so you can think of it this way. So on your universal covering, say, all of these three things are, say, copies of your initial manifold. You will start out in one with your Lagrangian manifold lambda 0. You start evolving it. It starts spreading out when you evolve it with your flow. And essentially, it will become larger as it spreads out. And this time evolves the Lagrangian now, I mean, is in a sense spread out on your universal cover above multiple copies of your initial manifold. But then if you project it down, you get exactly this phenomenon of being wrapped around your original manifold. So this is just, in a sense, a technical trick that is very practical. But with this time evolution, we essentially get the solution of this Hamilton-Jacobi equation. So these transport equations, they can be solved. I'm not going to go into much detail there, but it can be solved very explicitly. And you have, Subro, to your question, you keep excellent control such that for any m and l, that you can go to n sufficiently large, and you pay a price in the time until which you can evolve it. So t is restricted by a small constant times log of h, such that the difference between your ansatz and so until a fixed sufficiently large n and the actual time evolved state is in this CL norm, so is given still bounded by h to the power of n. So you give yourself an m, you give yourself an l such to control the regularity, and then you can find an n sufficiently large such that this holds. And the key idea is now the following. I mean, essentially what you see is the next step is we project back down. So here we have evolved our Lagrangian over multiple manifolds. So in a sense, it has evolved in this universal covering, but it will be spread out over multiple copies of your manifold. And then you project it back down. So it will live on your universal covering, and then you project it back down on your x to get the time evolution of your state on your base manifold. And here what happens is we can just take this u, this function u that we're actually interested in. Sorry, here there's a slash missing. So this is the projection. So you project it back down. So you look at the point x, you look at all the x tildes in the pre-image, and you essentially take your time evolved state at this x tilde, okay? And you project it back down. So this means that essentially you get a superposition of pieces of your time evolved WKB state. Okay, and maybe you can already see where this is going, because in the end we're going to prove a CLT. Because now and the number of these images on my universal covering here, this will be growing as h goes to 0. Plus, I mean, I'm not going to go into detail, but essentially the principal part of my amplitude is also small, so it goes to 0 with a certain rate. But I have essentially this combination of these oscillatory phases which do depend on my random parameter. Is this clear so far? So I've evolved it on my manifold. I get, in a sense, I can, by projecting it down, I get a superposition of a bunch of these WKB states. And the key observation here is essentially by looking at this phase. So there is something to prove here, but so this phi 0 is what happens is if I evolve any point on my Lagrangian manifold with the normal geodesic flow, which does not see the randomness, and I compare it with the time evolution. It blinks red and angrily. I'm sorry. And I compare it. Can I have 2 minutes? I heard that since I'm the last talk, we're not going to kick me out. So I compare it with the time evolution of this flow that has the randomness in it. And indeed, these two guys stick very close together. So this essentially is small until these times that are logarithmic in h. And if I look at this phase here, this with the randomness guy, so it has as a leading term, it has the phase that comes from the Lagrangian that has been involved by the geodesic flow. So it doesn't see the randomness, but I get in a sense here this part that with my small coupling constant delta, so this is small, where I essentially integrate over this, my symbol here, which is these random bump functions. And I integrated composed with the normal geodesic flow. So what happens is essentially, so imagine this is my phase space. So on some initial point, I just integrate along the geodesic flow, which I do here, okay? Some specific point. And as I go along, integrating from 0 to time t, I collect all my random variables that live in my little domains in my random potential along these bump functions. So this part is essentially some sort of random oscillatory phase. Okay. So going back to this local scale, maybe since I don't have much time, let me just skip this. So there is a nice way of rephrasing this phase, and just by skipping this, I present you this sort of final formula, which is this. After rescaling back to this local phase that I'm interested in, I get as a leading term this superposition of a lot of, with this amplitude here, which goes to 0 slowly, some deterministic part that depends only on the geodesic flow and my initial amplitude, and this random oscillations here. And all that is left then is to prove a CLT with these guys. I put this on this sort of last slide here. So for the CLT, you can just check that the expectation goes to 0 rapidly, and the covariance of this function is exactly converges to the covariance kernel that you would expect from this Barry Gaussian field. So with that, I am sorry I skipped a lot of things. Thank you very much. And
do you have questions?
yes. Sorry? Yes. So we do need the negative curvature here. There's a bunch of things that you need to prove that you know about, that you need to know about the usual geodesic flow. So essentially, the curvature is mostly reflected in the sort of ergodic behavior of your geodesic flow. I mean, it's even stronger on these negative curved manifolds. The classical dynamics, which is this geodesic flow, so you're evolving along geodesics, has the Anosov property. So essentially, at each point, you can decompose it into essentially into a direction along the flow, and there is a stable and an unstable manifold. So one direction that is kind of very contractive, and the other one that is very expansive. So, and there's a lot of geometry that we need to do.
The noise that you add, that Q in the first one where it is only on the position, right?
Yes.
So what's happening to it? Is it going to 0 or is it converging to white noise? I mean, if it.
Yeah. This noise here, this guy here. I mean, it is small. It's really converges to 0.
Oh.
Okay. So here this alpha. So in a sense, you can think of in terms of operators, this Q is bounded. I mean, it does oscillate, but not sufficiently strongly. But this H here really makes it a small perturbation. So the idea is simply not to go in similar to the Anderson model where you have a strong randomness appearing, but just to add a little bit of noise to help along. And the key feature where it actually helps is this little bit of noise helps us in. It's not strong enough to actually modify the classical dynamics. It just helps giving you a little bit of random phase to when you evolve your states.
Was there questions? Maybe I have one. In the statement of the main theorem, there is an expectation, right? You take the expectation of your random field. And is there a way to here?
Yeah.
Is there a way to have a convergence without this expectation?
So do you mean this? But this?
Yeah.
Yeah. No. This is the best we can do.
Is it, okay, it's not possible.
Yeah.
Okay, so let's thank the speaker again.
Well, thank you very much.